Hello there everyone, my name is Daniel Arnellis and today I'll be walking through WebWork homework number 10, problem number 16, a spring problem. To start out this problem, we want to find our differential equation, and to do that we're going to need our m, our beta, our k, and our function of t. So looking at the problem, we see that we have a spring whose constant is 2 pounds per feet, and it also says that the damping force is numerically equal to the instantaneous velocity. So the velocity is x prime, so we know that our beta will be multiplied by x prime, which basically just means that our beta is 1 if the damping force is equal to our x prime. We also see that there is no force being applied to this system, so our f of t is 0. Now to find our mass, we have to rely on the fact that force equals mass times acceleration for a vertical spring like this. So we input 4 pounds because it told us that our mass weighs 4 pounds. We set that equal to our mass times the acceleration due to gravity, which is 32. We solve for m, we find that m is 1/8 of a slug. Now we have our coefficients, so we can set up our differential equation. We put in 1/8 for m, 1 for beta, and 2 for k, and 0 for our function of t, and we have this equation here. Now, we need to start solving this equation using our method of undetermined coefficients. So we put r's in for our x's, and we solve for r, and we find that we actually have two identical r's equal to -4. So our generic equation will be c1 e to the -4t plus c2 times t e to the -4t. Now, in order to find the value of our coefficients c1 and c2, we now have to find what the initial position and initial velocity of our mass is. We read from the problem, the mass is initially released from a point, it should say, 1 foot above the equilibrium position with a downward velocity of 8 feet. Now, for these problems, usually we define downwards as the positive direction, so that we have a positive acceleration due to gravity. That's just how it's usually done, and that is how it's done for this problem. So now we know that 1 foot above the equilibrium position is actually -1, and a downward velocity of 8 is actually a positive 8. So to solve this problem, first we have to find the first derivative of our equation, and then we will input our values for the initial position and the initial velocity in order to solve for C1 and C2. So now we finally have our completed general solution for our differential equation. Now on to the three problems it asks us. The mass passes through the equilibrium position. It wants to know when, at what time t, the mass passes through the equilibrium position. So to find this, we'll know that it passes through the equilibrium position when x is equal to 0. So we set 0 equal to our equation. We solve, e to the -4t will never equal 0, so we can cross that out, and then we find that t equals 1/4 of a second. And for our next problem, we have to find at what time the mass attains its maximum displacement from the equilibrium. So to find that, we'll know that when it gets farthest from the equilibrium, the velocity will be equal to 0, because at that point, the mass will be moving farthest from the center position. It will begin to accelerate back towards the center position. For a brief instant, it'll stop moving entirely before it turns around and heads back towards the equilibrium. So we find our x prime of t, and then we set that equal to 0. Once again, we solve. E to the -4t will never equal 0, so we cross that out, and we find that our time is ½ a second. Then it asks us for the position at this time, so we simply put in 1/2 for t, and solve, and there we have our answer, e to the -2, and there we have all of our answers to our problem. Have a good day.